And so that's what we're talking about here. Everybody following this? All right, so what's a Turing machine? That's a Turing machine. At some point I Googled Turing machine and I downloaded this little image, and I'm surprised it's not running. It used to run. I don't know why it's not running right now. It's a GIF that runs. Right? Can we get it to run? No? The GIF's not running today. All right? That's a Turing machine. What is it? It has a table lookup, right? I told you that. But we're going to, instead of using a table lookup, we're going to use this finite state graph thing. That's going to be encoding our table. All right? So it has these finite states, and it has an infinite tape. Actually, it's usually fixes at one end and it's infinite in the other direction, right? Why is it infinite? You're never going to use it all, but as the input gets, if you have bigger and bigger inputs, you might use more and more of it, right? But in a finite amount of time, you're only going to use a finite amount of it. And so we have to say, if it's a model of computation, we have to say, let's talk about our kind of a loop invariance, right? If we stop time, what is the state or configuration of the machine, right? What are we storing, right? So what's the difference between state, in this context, state, these are the states that it's in, and configuration is also going to tell me what's the contents of the memory, of the tape, all right? So we're going to have if I want to say what's true right now in time, it's what's the current content of the tape, right? It's going to change through time. And oops, did we hit the end button? We might have hit the end button. Turing machines. Oh, we did that one already. All right, we're somewhere about here. All right, so what do we got? Contents of the tape, right? So let's talk about the tape. Each cell in an ideal restricted Turing machine can be a 0, a 1, or a blank. Somewhere in my brain I was thinking that they could be only 0, 1, but you initially want the tape to be blanks, and it's awfully nice. It's helpful to be able to write blanks later on. If you're restricted to writing 0, 1s, its coding can be hard, right? But we can prove that if I let you have a more complex alphabet, right here, its symbol is a sigma, and we're going to use it to mean your alphabet. So it could be ASCII, right? It could be binary. It could be 0 to 10. It could be whatever alphabet you want. But it needs to be, the designer of the program needs to tell you what your fixed alphabet is. All right? And then each cell of the tape contains something from that fixed alphabet. And one of the things we will do this to prove, quote prove, is that if a Turing machine with ASCII Turing machine can do it, then we can compile it into a Turing machine that's binary, right? So that's what you need. And then the tape is, as I said, it's infinite in one direction. But after a finite number of time cells, that's all all right, after, you've only used so much of it, and the tape arrives blank, right, at the end, right? Initially, the input is stored in the first cells, right? So generally, we think about the input being a binary string, but again, the input, you can have any alphabet you want, right? So you can talk about the tape alphabet, and you can talk about the alphabet of the language we're trying to, the input. So you can choose whatever, your alphabet could be A's and B's, or it could be 0 and 1s. It can be any alphabet you want. Here, I've used B to mean blank, right? Because if I left it blank, you wouldn't know there was a blank there, right? So I'm saying that we're going to start with the single blank at the beginning. Well, there's other nuances about your Turing machines. We're going to talk about a head. If a head goes past the beginning, what does it do? We could change that. But we could also design it so that your algorithm never goes past the beginning. Right? So there's a blank there to tell you this is the beginning, then the input followed by an infinite number of blanks. Right? That's how we're going to present the input. Everybody follow that? And how do you get an output? Oops. There are two ways to get an output. All right? Here I'm implying that the way you get an output is you leave the output on the tape. But another option, if the output is a yes-no thing, right, then the Turing machine could go in test states. It could go into the yes state. It could go into the no state. That's another option. All right. Oh, I didn't tell you the head. Surely the head will come up at some point. Surprising I didn't have a head. Did we talk about head? No. Just in case the head got lost, how does the machine access the tape? It has a head that it can move the head left or right. Now, can your finite machine know where the head is? No, because it only can know a finite possibilities, right? And the head can be anywhere, right? So it can't know where the head is, but it can move the head, right? That's the head. Current state. All right, so the machine has a finite set of states, right? And as I said, we could name those states Q1, Q2, Q3. It's just a bunch of nodes, right? And we put a red dot there to say at any point in time, the Turing machine is in one of those states, right? Everybody following this? Right? And there's a fixed number of states. It's a finite, fixed. This graph is built by the designer at compile time, right? The tape gets changed at runtime. But that graph is our table lookup thing. It's designed at compile time, right? It has some fixed number of states that are designed at compile time. Right? Everybody following that? And at any point in time, we're in one of them. Right? Right? One of the states has a little arrow associated with it. And that one is going to be our start state. So when we start, we need to, from precondition, we have to establish the loop invariant. How do we start? We start in the start state. Right? In fact, we start with the input on the tape and the state in the start state. Right? Yeah?
Do we count as we walk from the start state? Each time we go to the next state, do we count as the head?
We're going to have different instructions. You could do different things. All right? So this one has no out edges, and I guess that's going to be the halt state. So there's at least one state which is going to be called the halt state. And when it halts, then hopefully the answer is on the tape. And you could have two types of halt states. You could have the answer is yes, and the answer is no, halt states. Or you could have the answer on the tape, doesn't matter. Right? Here we got the head, right? There's the current location of the head, and it's going to move, right? Now, and the Turing machine is able to move it left and right, right? And here the question: does it know the current location? Well, let's go back to maybe this is why I left it till later. All it knows is what state it's in, right? And there's there's only a million states. You have to choose a billion. There's some number of states. There's only that many. So it can only know so many different things. And so it can't know all the places the head could be. Right? So it does not know the location of the head. Right? It doesn't know. Right? What it does know is it knows what values in the cell where the head is. Right? In fact, it doesn't know what's on the tape. Right? It only knows the value on the tape where the head is. That's all it knows. Right? Everybody getting this? Right? And what are the legal operations? So now I've told you where we are, right? I'm now going to tell you how to take a step. All right? Legal operations is, what do we know? We know our current state, right? We know the value that's in the tape at the cell that the head's at, right? So here, I'm in this state, and I'm reading a 0, right? That's what I know. In fact, that's all I know, right? All I know is I know what state I'm in. I know what character I'm reading. So, remember table lookup? We're going to do table lookup, right? Or this transition diagram to tell me a bunch of things. It will tell me what state should I go in next, right? It'll tell me what character should I write on the cell where the head is, right? The cell where the head is had a C. I can change it to something else, right? Does that make sense? And I get to say, move the head or move the head left or move the head right. Right? Does that make sense? That's all you're able to do.
So if you read a 1, it would just go back to Q1?
Yeah. So you can say, I guess if it read a 1, it stays in state Q, but it replaces it with a 0.
But it has like the left arrow.
So it writes a 0 and moves over to, the right arrow is moving the head, right? The arrow tells you how to move the head, not how to move the state, all right? So if you're in Q1 and you're reading a 1, then you write a 0 where the 1 is, you stay in Q0, in state Q1, and you move the head right, so now you're looking at a different cell. Oh, yeah, never ask me to know my left from my right. Right? Because I'm just that Pooh Bear.
And then like the solid black arrows is the change of states.
Yeah, the edges between the states tells you how we change state, and the 2-line arrow tells you whether to move the head left or right. And you'll know I didn't say you can leave the head stationary, but I'll be flexible. You can leave, if you want to pause and contemplate life, you can leave it stationary. But there's no purpose in leaving it stationary because I'm not gaining any information, right? What's there is what I knew is there. So really, I want to learn something new to move forward. Yeah? No. We can later talk about new types of Turing machines, right? But this type of Turing machine moves left or it moves right, right? So everybody see that this is a very simple machine. Yeah?
The direction of the head tells you whether you're moving left or you're moving right.
Two things are moving. I'm changing state, and that's told how I move state is these. So don't get hung up about this notation. I stole this picture from the web, and we don't need. This is not the notation we're going to use. All right. But this notation says if I'm in this state and I'm a 0, I follow these instructions. And if I'm in this state and I got a 1, then I follow these instructions. Right. Right here we go. Here I'm in this state. So this tells me my current value. This tells me what value do I write onto the tape. Right. This value tells me the direction I move the head, right? And this tells me what state I'll be in next, right? That's the notation I got off. In fact, I think we're going to, Wolfram Alfram lets you put in Turing machines and they run for you. And this is the notation it uses. Yeah?
So when you say move the head, are you talking about like moving that red arrow?
This red arrow moves to the next cell. Yeah. All right? So the more formal notation is this. There's a thing called the delta function, which is basically table lookup. And it takes two inputs. It takes your current state. It takes the cell the value of the cell that the head is looking at, and it returns three things. It tells you the next state to be in. It tells you the character to write where the head is on the tape. It tells me whether I move my head left or right. Right? And if you're bored, I'll let you stay stationary. Right? Everybody get that? Right? So given the current state, given the current value that the head is looking at, the table has a preset table. Remember I talked about constant tables? It tells you the next state. It tells you the character to write in the cell. It tells you whether to move the tape head left or right. Right? Everybody got that? And here's a table. Right? So I built this little table here. Right? In fact, this little table, I think, encodes the same Turing machine, if I'm not mistaken. Right? It says, if I'm in state Q1, and here's the state I'm in, here's what I see on the tape, right? If I'm in state Q1 and I see a 0, so I'm in state Q1 and I read a 0, what do I do next? I move to state Q2, I write a 0, I move the head right. Right? Does that make sense?
So does it write before it moves the direction?
Yeah, you write and then move the head. Right? And the reason you want to do that is because when you move the head, you learn a new thing. So what you do next depends on what you knew. Right? That's why there's no point in staying still. Because if you stay still, I know it's there. Either it was there or I wrote it. Right? So I'm just spinning my wheels a bit. Yeah? All right, so, it doesn't necessarily read it all. This is a very little example, and we needed to demonstrate the various ideas. And no one, maybe the problem is the third character a 1? So you have to go to the third, you count to the third character, you see if it's a 1, you say yes or no, you halt. You don't have to read the rest. Everybody good? Yeah? So at the beginning, you're in the start state, and the tape is the input. Then it runs, and it stops when it gets to the halt state, and then the output is the output. The tape contains the output. Right? Does that make sense? And hopefully, I'm expecting you're thinking, how can you compute anything with this? Right? How can you compute anything with this? And so that's what we're gonna do the next couple lectures is work on compiling Java program. You give me any Java program, we're going to work on compiling it into a Turing machine. All right? Yeah.
So in this specific diagram, what this specific Turing machine is, would Q0 be the start state or not?
Yeah, because it has the little extra arrow. The arrow that comes from nowhere is the start state. Right? Everybody good? Yeah?
And instead of having a linear set of states, each of which...
Did you say linear?
Well, it's like there's either a loop state or a next state for each of those. You could have like Q0 instead in Q1 or Q2?
Yeah.
Okay.
Yeah. Its graph has a finite number of nodes. Every node has a 0 output and a 1 output. In fact, if the tape is ASCII, then it has 256 edges, right? And that graph can be any graph you want. Right? Everybody good? Right? Current state, what's on the head, then the table presents what's the next state, what do I write on the tape, how do I move the head, the tape head. Right? Everybody kind of get it? So, in general, when we teach a course, it's really good for you to learn what we've done, right? So between now and next class, you should know what a Turing machine is, because we're going to be using them, right? And so you should know what it is. Yeah?
It's possible the Turing machine keep running and running and never stop.
Yes. Yes.
So just go back between state Y, state T, then.
Yeah, it could go, well, in fact, we can see now that there's two things it could do. It could keep the head in more or less the same place, and it could cycle in the states, right? That's one option. Or it could keep using more and more and more of the tape, right? If you just said, tape, move right, then it'll go forever, right? So, I mean, there's different types of, right? Everybody get that? Machines can definitely run forever. And that's why the halting problem is, what's the halting problem? I give you a Turing machine and an input, and I ask you, will this Turing machine halt? And that's an undecidable problem. Right? Everybody good? Right? So what is a Turing machine? That's what a Turing machine is. Right? Nothing more, nothing less. Right? It gives you the instructions for computing. It's abstract. Right? It's not practical. That's what a Turing machine is. All right? And so what are we doing now? Oh, it's starting to. Here I'm running it. All right. So if you wanted to, you could say, well, I'm in this state. I'm reading a 1. So what do I do? Right? I kind of somehow I don't know. We don't want to do this. You can trace it out in the courtesy of your own home. Right? You can trace out this Turing machine. Does that make sense? Right? And here again, if you go to Wolfram Alpha and you ask for a Turing machine, it gives you some standard ones and you can put your own in. And, I lied to you. This is how it stores it. So how it stores it is, in this case, there are two states that I can be in. I can be in my drop is pointing up or my drop is pointing down state. Those are two states. And the tape is going to have either 0 or 1. And 0 is going to be white and 1's going to be gray. Right? And then, based on your current state and the color of your cell, where the head is, it's going to tell me, and how do we store that? The head, this is a standard thing that we do, right? How do I tell you where the head is? I'm going to put the symbol representing the state there, right? So this little water droplet tells me two things. Tells me my head's there, that's on the tape, and it tells me I'm in the upstate, right? And so right now, I'm in the upstate and my cell's white, right? So this is what I do next. What do? I go into the downstate, I paint the cell I'm in gray, and I move my head right, right? So let's see if, right? So that's what it's saying I do. And so here, look at, I painted it gray, and I went into the downstate, and I moved my head right. Everybody see how we did that? Right? So now I'm in the downstate, and I'm looking at a white guy. So what do? I'm now going to have up. I'm going to paint it gray, and I'm going to move left. So what's going to be? It's going to now be that. Does that make sense? And then now I'm in the upstate, and it's gray. So I paint it white, I go down, and I move left. Everybody following this? So you can keep doing it. Right? You can keep doing it. And this is what it does. All right? Does that make sense? And then you might ask, will this machine halt? Well, you look at the pattern. It looks like it's swiping back and forth bigger and bigger, and it's going to do that. If the tape's infinite in both directions, it'll do that forever. Right? If the tape's bounded on one side, maybe it'll hit that side. Everybody get this Turing machine? Yeah?
So you said that we can change the type of input to ASCII or
Yeah.
text.
Yeah.
So that changes the clock cycle by a lot.
Well, we're still going to talk about clock cycles. I was only kind of making a joke that if you made a complex operation, then the clock cycle would be slower. We're not timing our Turing machines. Everybody good? Yeah? If you go left and you hit you hit the beginning, well, you have to define what you're going to do. I've heard definitions that if you run off the end of the tape, then your machine blows up, which is considered to be a bad thing. Or you could somehow have your machine be kind and say, hey, you hit the beginning, you better do something else. Right? Or maybe it can bounce. I don't know. You can decide what your Turing machine wants to do. Generally, we'll try to design the algorithms so that they don't hit the left end and they do halt. Right? Everybody good? All right, so now our input is considered to be generally binary, right? And then we have this spaghetti Turing machine that just does these transitions, right?